Ladies and gentlemen, this class recording has started. So, the top title for today's outline is called chemical energy. So let's start with that. First, forgot to do some things. Right. Good. Question: how do we define energy? Ability to move or change matter, right? Good. We can all read. Excellent. So, we also talked about energy in terms of what? As far as like our working definition of energy, the ability to. Let's not go with do work because that has a specific meaning, right? Do stuff, change stuff, make things different. What we find out is that there is a certain, and we talked about a bunch of different types of energy, right? Chemical or kinetic energy and gravitational potential and elastic potential. So this unit, we talk about a new type of potential energy that's called chemical energy. And like its name suggests, it's the energy stored in chemical bonds of a compound. Going back to the beginning of the last unit, why do atoms bond with each other? To get 8 valence electrons. And 8 valence electrons is important because it's stable, right? It is a low energy state, right? There is energy that is released in that process a lot of times, okay? But what we also find out is that there is energy that is associated with those two things being connected to one another. Yes, it is a low energy state, but you are holding together two atoms. Atoms are composed of protons and electrons, right? While the protons of one atom are attracted to the electrons of the other atom, do the electrons of atom A like the electrons of atom B? Does the nucleus of atom A like the nucleus of atom B? No. So there is some energy there, even though being bonded is less energy than being separate, there's still some energy there. And it's specifically, it's potential energy, because we said our general definition of potential energy is energy of condition or position, where or how something's put together. So chemical energy is associated with the position of those atoms bonded to each other. Okay? Good there? All right. When we talk about a reaction, what happens in a reaction? Give me a 2-cent definition of what happens in a chemical reaction. Things change, right? We start off with something, we make something new, right? Eric, why is that going to happen? Got some help? Liam, good. Well, most of the time they're probably already at 8 valence electrons, right? If they start off that way. But you're thinking along the right way, right? Why would a chemical reaction happen? Why is 8 valence electrons important, Liam? Someone can help him. Why is 8 valence electrons important? Other element can make the compound have different properties. Lowest energy state, right? 8 valence electrons is a low energy state, but sometimes when it's joined together with something else, it might be even lower energy, right? It always comes back to that. So, chemical reactions involve the breaking of chemical bonds in the reactants and the formation of chemical bonds in the products. Chemical reactions involve the breaking of chemical bonds in the reactants and the formation of chemical bonds in the products. When you're done writing that, flip over your paper. When you're done writing that, flip over your paper. flip over your paper. Keep it on the back side. This is propane. Okay? Propane undergoes a combustion reaction. Right? So, there's space down on the back side, like in the bottom left and right hand corner. You might want to write this down. Okay? Alright, so propane undergoes a combustion reaction. Knowing what you know about combustion reactions, what does propane react with? Oxygen. How does oxygen come? Diatomic, right? So, there's the combustion of propane. Okay? Those are the reactants. Propane is a specific type of chemical, or a specific type of compound that we refer to as a hydrocarbon, right? When hydrocarbons undergo combustion reactions, there are two products. Do you remember what they are? Carbon dioxide and water. Alright? So there is the chemical equation. I should have wrote that up on the board so that actually people watching the recording could see that. Okay? Here. So here's propane. This is the combustion part. Because propane is a hydrocarbon, these are the two products. Okay? Good there? Yes, Dave?
Is it safe to breathe non-diatomic oxygen?
No. Non-diatomic oxygen is actually very reactive, and it will start reacting with stuff in your body, but it's so reactive that it really won't get into your body. It'll find something before it gets there. So, that's... You probably don't have to worry about that too much. So. All right, balance it. Go. You can work with the person next to you if you want to. If you don't want to, that's cool too. Alright, answers up on the board. If you don't want to see it, don't look yet. Let's take 30 more seconds. We're still working on it. So we kind of talked about in a situation like this, we should start with carbon and hydrogen, right? Because they only appear in one formula on each side of the equation. Save the oxygen for last, okay? All right, good there. Okay, question. And David, this kind of builds off of the question you just asked me. Is that stable? Is O2 stable? Yeah. We talked about that when we were first talking about bonding, right? Oxygen finds another oxygen to bond with. They share electrons. Everybody's got 8. Okay? Is this stable? Yeah, that's why it happens. Okay? So, if we just mix, well, let's do this. In order to make the products of this reaction, what do we first have to do? In order to make the products of this reaction, what do we first have to do? some of you I talked about yesterday during the lab. Let's go with a Lego analogy, right? All of the atoms that show up in this equation are like pieces of Lego. We can make a bunch of things out of Legos. Let's say you make a house out of Legos. And then you decide you don't want a house out of Legos, you want to make a car. What do you have to do first before you make your Lego car? You got to take the Lego house apart, right? Oxygen, diatomic oxygen, is stable. Propane is stable. But if we want to make those products, what do we have to do first? Take them apart. Then rearrange them, right? So, that's why we say chemical reactions involve breaking of chemical bonds in the reactants and the formation of chemical bonds in the product. Flip it over back to the front side. So that graphic right in the middle of the page represents the combustion of propane, right? That's why I had you flip it over. I didn't want you to just cheat because it has the balanced equation right there. Okay. So, before we make the carbon dioxide and the water that are the products, we have to break apart the propane and the oxygen. Okay? But, even though it doesn't show up in the chemical equation, what else is a product of this reaction? Heat. Why would we break apart these 5 oxygens in this propane and rearrange them this way? Why does that happen? Liam, why does that happen? Ali, why does it happen? Gets them to a lower energy state. Alright? And we see that because what else is left over in the products? There's some extra heat, right? Where was that heat before? Well, it was part of the chemical energy that makes up these bonds. But the chemical energy in these bonds is lower than the chemical energy of these bonds. But what do we know about energy as a whole? It's conserved, right? So if we have less chemical energy in the bonds, there's got to be some heat left over. Right? Does that make sense? But, okay, so let's go here. Alright, we classify reactions according to what happens in the energy as either exothermic or endothermic. And because you know English, you probably can describe what happens in that, right? Okay? In exothermic, what happens? Heat is given off, right? Heat is released. Whereas in endothermic, we have to store heat or gain heat, right? The graph on the left is an exothermic reaction. Let's analyze it. Y-axis, chemical energy. X-axis, reaction progress. So we can think of it as time, too, if we want to think about that, right? Reactants are here, products are here. What is the graph telling you about the energy of the products versus the energy of the reactants? It's lower. That's fine. Products can be lower than reactants. In fact, that's why a reaction should happen. But if the products are going to be lower than the reactants, what else has to happen? If the products are going to have less energy than the reactants, what else has to happen? Heat. We have to give away that extra heat, right? The difference between the energy of the reactants and the energy of the products is how much energy is released. Okay? Does that make sense? On the other side, reactants, products, right? But what do you see about the energy of the reactants versus the energy of the products? Which has more energy, reactants or products? Products have more energy, right? This is the difference between them, is how much energy we have to pick up to make that happen, right? If we go back to the Legos, okay? Let's say you make a short little house of Legos, but then you want to make a tall tower of Legos. Is the tall tower as stable as the short little house? Not really. Can you make the tall tower? Yeah, right? You got to put some work into it, but you can do it. Same thing here. Can we make a product that has more energy than the reactants? Can. You just got to put energy into it. Does the tennis ball go up on its own? Can I make it go upward? Yeah, but what do I got to do? I got to do work on it. Whether you meant to say that word or not. I got to do work on it, right? Increase the energy. Does that make sense? Okay. Most reactions fall into which category? Exothermic, right? Lower energy. We tend towards lower energy, right? But let's examine. Do exothermic reactions happen on their own? Most cases, no. If we mix propane and oxygen together, do we automatically get carbon dioxide and water? No. Look, ready? Propane comes out of there. It mixes with oxygen in the air. Do we make carbon dioxide and water? No. We know there are 3 requirements to make a fire, right? You need fuel, you need oxygen, but you also need what else? A little heat, right? When we look at this graph, here's the reaction of here's the energy of the reactants, right? What's the first thing that happens to the energy? What's the first thing that happens to the blue line? It goes up. Meaning, what do we have to do to those reactants to get them to react? What does this blue line going up represent? Gaining energy, right? Here, we got to gain a little bit of energy in order to do what? Well, eventually, yes, lose it. But why do we have to gain that energy? To get the reactants, what has to happen to those reactants? If we want propane to react with oxygen, what did we say was the first thing that we got to do? Add heat, because physically what has to happen? If we want to build a Lego car, what do we have to do first? Take apart the Lego house, right? This little bit of energy here, right, goes into separating all of these atoms that are already bonded. Does that make sense? Right? Before you, to light a match, what's the first thing you have to do? Strike it, right? What are you doing to the match? Friction, adding energy, right? To get it to start, but once it starts, what happens? It's all downhill from there, right? Does that make sense? Donna, go ahead.
So are you basically saying that like a chemical reaction can't occur without energy and heat?
In most cases, yes. So Donna said, does that mean that you can't get a chemical reaction without adding heat? But let's go with any kind of energy to begin with, okay? Because it doesn't necessarily say heat over here, it just says energy, right? In most cases, yes, right? Things that are flammable. There's a bunch of flammable things in this room, right? They don't just spontaneously start combustion reactions with the oxygen in the room. We need something to kind of get that reaction going. Something to separate the bonds of the flammable stuff and the bonds of the oxygen so that they can rearrange into carbon dioxide and water. Does that make sense? Right? In the case of your Bunsen burner, what's the energy that you have to add to get the reaction to go? Fire, right, that comes in the form of what? Heat from the... What do you have to do to get it to start? That's the match, right? Okay? Okay, good.
So if you were using the example of the match, like in the first picture,
Yep.
like the hill would represent like the friction that you're using, and then the down. Okay.
Yep. And then, so yeah, so if we use the example of the match, the friction is the little uphill, the fire that starts is the downhill, because that's the energy that's being released. Okay? We refer to this little bump as the activation energy. refer to that bump as the activation energy. Right? The little hill that we have to get over to make this thing start. Right? There's activation energy for endothermic reactions too. Just how big is the activation energy? Activation energy for an endothermic reaction is really big, right? Because we're increasing the energy of those products. Okay? Does that make sense? Okay. So down at the bottom, right? I don't know if I actually did I put that in there? Oh, I apparently didn't put it in there. So down at the bottom, okay? Fill in Roman numeral 2, letter A, exothermic, energy released as heat. Exergonic is energy released as something else, some other kind of energy besides heat. Could be light, could be sound. Okay. And then B, heat is added to a substance. That's the definition of a what? Endothermic reaction. And then the final term that shows up there, endergonic, energy in a form other than heat is added. Anybody ever been to the dentist recently and got a filling? Anybody? You guys all have your little sealants on your teeth now, so you guys don't get cavities anymore and stuff like that. But anyway, if you ever get a filling sometime in the near future, or if you remember this in the past maybe, the dentist will drill out the little cavity part in your tooth, right? And then he fills it with a little plastery kind of thing, okay? But then there's this little pen that he has that's like it like shines it in your mouth on the stuff that he put in the little hole. That pen gives off ultraviolet light. That energy goes in and makes those plastery things react with one another and turn into some hard cement stuff, right? That's a example of a reaction that uses light instead of heat to get it to go. Okay, good.
Is that like the same concept when you get braces and you like the breath and you put the like pen over it?
Yeah, same thing. Yes, yeah. It's just it's light that is so the adding of the energy, it doesn't always have to be heat. Sometimes it can be light that'll get that energy, that'll get that reaction going. But yes, same concept. Okay. All right, good there. Okay, on the back there are 4 energy diagrams. Okay. Talk to your partner. Sorry, they didn't copy real well. They're all 4 up here on the board. Okay. So, talk to the person next to you and answer questions C and questions D on your outline. So, which of the energy diagrams is exothermic, which are endothermic, and which is the most likely reaction to occur? Discuss with each other. Go. Or just figure it out by yourself. You got them right. according to my pictures up here, the two on the top are the first two that you guys have on the left-hand side. Those are both what kind of reactions? Those are both endothermic reactions, right? Why, Austin? You're right. Ollie, go ahead. They end up with more energy than they started with, right? Meaning the products have more energy than the reactants, okay? And that means the two on the bottom, which are the ones number 3 and number 4 on your sheet, those are both exothermic reactions because the products end up lower than the reactants. Good there? Okay. Which of these reactions is the most likely to occur? I know at least a couple people have the right answers. I saw that walking around. Ollie, go ahead. Bottom left, or on your guys' sheet, that's number what? 3. Number 3. Why is that one most likely to occur? There's 2 ways you can answer that question. Both of them would kind of be equally right. Why is that reaction the most likely one to occur? There's 2 ways you can go about answering that question. It's right. That's the right answer. Okay. Why is that the right answer? It requires the least amount of, let's add one word to that statement, the least amount of activation energy, right? The hill at the beginning of this reaction isn't very tall compared to the hill in the bottom right. Does that make sense? So it's the least amount of activation energy. What else could we say? There's another way that we could answer that question too. Really good. It loses the most energy, right? Why do things react with each other? To get to the lower energy state, right? The one in the bottom left, or the third one in yours, there's the biggest difference between start and finish. Both of those, the biggest difference between start and finish and a lower activation energy. Both of those are good indicators that something is likely to occur. All right? Does that make sense? Good with those? All right. Let's talk about reaction rates. We think we've discussed this before, but if we haven't, we'll just do it now. When we talk about something being a rate, what does that mean? Whenever we describe something as a rate, there's a certain factor that is implied with that description. Time, right? Whenever we discuss rates, we're always talking about time. How quickly does something happen, or how much does something happen over time? So there are things that we could do to make a reaction go faster. All right? What are some things we could do to make a reaction go faster? Temperature, right? Specifically what? Higher temperature, right? So, if we increase the temperature of something, right? So, sorry. Reactions go faster at higher temperatures. We should change that to faster, because fast is kind of a relative term. Okay? Why do reactions go faster at higher temperatures? What did you say before? I thought is that what you said before? Oh, I thought you said something different. Why do things go faster at higher temperatures? What happens as things start getting hotter? What happens to the particles as things get hotter? They move more, right? And if they move more, what do they do to each other more? They hit each other more, right? And that's reaction, okay? Number 2 on that list, stirring, right? What is stirring? Mixing up, right? What do you do to the particles in something when you stir it? You make them go faster, and you make them run into each other more, right? So temperature and stirring are pretty much the same thing, right? You just make the particles go faster, okay? All right, next, surface area. A large surface area for reactants will speed up the reaction. That generally means, what do we do with things if we want to increase their surface area? How do we increase the surface area of something? Lucky for me, I haven't cleaned up our lab from last week. Here's a sugar cube, right? There's this sugar cube, and I could get like a scoop of sugar, right? They could have the same mass, the same amount of sugar. But what's true about a lot of the sugar in this sugar cube? It's bonded together, yes. Is it available to react with other stuff? The stuff on the inside can't react with other things, right? Because it's not on the surface. How do we increase the surface area of the sugar cube? Spread it out or smash it up, right? Put it into small little pieces, okay? That means more sugar is in contact with more of the other reactant, whatever it might be, right? I shouldn't say nobody. Hardly anybody uses sugar cubes. Do you guys even have sugar cubes at your house? Right? So at church, like for tea time, is that like crushing up sugar makes it dissolve much faster than putting a sugar cube in something, right? Also, concentration. That means how much stuff is there, right? If we have a more concentrated solution, things will go faster, right? Because there's more stuff there. In terms of our lab from yesterday, your hydrochloric acid that you used was 6 molar. That's pretty concentrated. That means there's a lot of acid in that solution. There's a lot of water too, but there's a lot of acid. When you put the hydrochloric acid into the zinc, it started bubbling right away. If I had a lower concentration of acid, would we still get bubbles? Yes. Would it bubble right away though? Might not happen as quickly, right? You'll still get bubbles, but you won't get that vigorous like fizzing that you saw, right? That happens too with gases, but when we go at higher pressure, the gases, that correlates with a higher concentration. All right, good there? So those are all physical things. We're not dealing with any of the reactants of the reaction in any way. Okay? But there's some chemical things too. Right? First, size of molecules. Okay? Bigger molecules react more slowly than smaller molecules. Okay? You ever hear about whole grains versus processed grains? Hear about that like on the news or like in commercials and stuff like that, right? Big, long molecules take a long time to react. That's why people who do endurance events like triathlons and stuff like that, they like those long molecules because it breaks them up a little bit at a time. It takes them a long time to break up that way. They're big, long molecules, so that breaking up those molecules releases energy more slowly over time. Right? But athletes who do not endurance events, but sprinting events or like short burst things, you don't want those long molecules. You want like quick, short little sugar molecules, right? Like glucose tablets and stuff like that. Yes, no, maybe? Am I getting off the track here? It happens. That actually wasn't what I meant. All right, and then the last thing is a catalyst. Okay? A catalyst is something that changes the reaction rate without being consumed or changed significantly. It's something that makes the reaction go faster, but it's not actually part of the reaction. Okay? For example, so let's go back to elementary school, okay? Maybe middle school, probably more elementary school, right? Yeah, I don't know if this happened. It didn't happen a whole lot when I was in elementary school, but let's say, right, there was one of those days when these two kids were just getting mad at each other, and everybody knew they were going to fight. So they met by the bike rack after school. Yes? Yeah? Come on. I know, that never really happened. This is like an old example, right? Okay, but imagine there's two people that are thinking about fighting each other. Okay? And so they stand there and they kind of like, they're kind of like giving each other the eye, who's going to be the first one to throw the punch, right? And then somebody says something about the other person's mama, right? Okay. So, but the catalyst in this situation is the guy who's not going to fight anybody, but he just stands there and he's like, oh, did you hear what he said about your mama, right? And then another guy's like, oh, are you going to let him tell you that, right? He's not the one who's fighting, but he's going to make the fight start sooner, right? Does that make sense? Yes, no, maybe? Right? Okay. That's a catalyst. Something that makes the reaction go faster, but without actually being involved in the reaction. The guy who stands there and talks to the two guys who are fighting, right? So I shouldn't stereotype like that, right? Okay. Girls could fight too. Right? It happens here sometimes. But, right? That person isn't going to get suspended. The two people who are going to who fight are going to be suspended. That guy's going to be fine, right? So, sometimes we have catalysts go both ways. It can change the reaction rate. Sometimes we slow down the reaction. We have what we refer to as an inhibitor. Right? It slows down the reaction, or it increases the activation energy. If you look at the picture, if you look at the graph down at the bottom of the page, right? This is reaction rates with a catalyst and without a catalyst, right? Notice it changes the size of the hill. It changes the activation energy, or what they refer to as the energy barrier in this graph, right? The green is the one with the catalyst. It lowers the activation energy. But an inhibitor works the other way. It would make the hill bigger that you have to get over. Okay? Good there? And finally, we have what we call an enzyme. An enzyme is a biological catalyst. Sometimes we have reactions that happen in your body that we want to go faster or we want to go slower. Enzymes will make those things happen, either faster or slower. Okay. So, enzymes are basically biological catalysts. Okay. All right, good there? Tomorrow we'll do acids and bases.
Is that in Gatorade?
Catalysts?
No, the last thing.
Enzymes?
I think I saw it on the back.